All right, so there's a whole lot of matter out there, a whole lot of different types of matter. So naturally, what we might want to do is categorize different types of matter. That way we can explain its properties without having to look at every single thing and completely, categorize or completely explain it. So we can have phases of matter, which will explain a lot of the properties of a compound. So phases of matter are just common ways that our molecules or our atoms arrange. And what we're talking about here are mostly solids, liquids, and gases. Of course, as we said earlier, you have to be careful of categories, but these are by far the three most common categories. So if we think about our phases of matter, they have different macroscopic properties. So macroscopic properties is just basically zoom out what's going on the big level. So let's say we have 3 containers. Just going to draw them shaped like this. It's supposed to be like Erlenmeyer's, but it's pretty bad rendition. Not the greatest artist, but you get the picture, right? And then we're going to put different types of matter in here. So right on this left, we'll go with a solid. In the middle, we're going to put some kind of liquid in here. And then on the right, we're going to put some kind of gas, right? And then we're going to see kind of what they do. So if we put a solid in here, let's say it's a square. The square will stay a square, and it's not going to use up all the volume of the container. If we put in a liquid right here, the liquid's going to pour. It's going to go from the bottom all the way up to as much as you fill it. And it'll generally take the shape of the container, right? If you pour it into something spherical, it'll appear as a sphere. If you put it in a more square-like container, it'll appear more as a square. But it'll only fill the bottom up until you have enough liquid. And then finally, on the last one, we'll put a gas in here. So when we fill it up with gas, this gas is going to spread everywhere, right? It's going to take up all of the container. So in general, what we say is that solids have a fixed shape and volume, right? No, but even though we put a square in there, it stayed a square. Liquids have a fixed volume, right? Just because we have a bigger container doesn't mean that the liquid's going to use up more room. It's still only going to be able to take up as much room as we have in terms of the liquid, but it's got a variable shape, right? It's going to take up the shape of the container. And then finally, with a gas, we have both a variable shape and volume. The gas will take both the shape of the container and it'll take up the entire volume of the container. You give it a bigger container, it's going to occupy more room. You give it a smaller container, it's going to occupy less room, right? So we see different macroscopic properties, and what we want to do as chemists is zoom in on the molecular level or the intermolecular level. So we might want to ask ourselves why. Why do solids have a fixed shape and volume and gases don't? And it all has to do with the arrangement of the molecules. So we think about H2O, right? H2O can exist in multiple different types of phases, right? We can have solid H2O. We know that as ice. We can have liquid H2O. We know that generally as just water, or we can have gaseous H2O, which we can call different things, maybe water vapor or steam. I'm just going to call it steam here. You can call it different things, right? But H2O can exist as multiple different things, right? So when we've got solid H2O, we've got ice. And if we put that in a container, it's just going to look like whatever it looked like before we put it in the container. In this case, I made it a cube. So we're going to want to zoom in here and think about what's going on the molecular or the intermolecular level. So whenever we have a solid, all of our atoms are in fixed positions and they're packed as tightly as they can be packed. So when we think about solids, we think about the molecules vibrate. So they're still moving, but they're not changing places with one another. They're just kind of vibrating about a fixed position. So they're just vibrating in place, but they can't move or they can't switch spots with one another. Then we go ahead, heat this ice, and we end up with some liquid water. Right, that's going to take the shape of our container, but not necessarily all of the volume. And so we're going to zoom in and see what happens here. So in liquid water, our atoms are still touching one another, and there's not really much space between them. However, what they're doing is still moving around. Now, instead of vibrating about a fixed position, what we say is that they roll around one another. So now they're free to change places, but they're still touching one another, right? And that explains why the liquid takes the shape, but not the volume of a container. And then finally, we have steam. So we're going to draw a closed container, otherwise all of our steam would leave. And so in this case, steam, it's going to take up the volume and the shape of the container. So let's think about why that happens. So again, back to our kind of molecular level, what we have here is just our molecules are just flying all around the place with a huge amount of area in between them. Sometimes they'll collide and bounce off of one another as well. So what we say for gases is that molecules fly around all over the place, right? Every now and then colliding with one another. So in general, if you think about ice, in general, we do go from a solid to a liquid to a gas as we heat, right? And instead of saying heat, we're going to say that we add energy, right? So when we increase from the left to the right, we add energy, right? And that makes sense. You go from ice, if you put some ice in the microwave, you go from ice to water to then eventually steam. Right, you go from a solid to a liquid to a gas. So a big goal of chemistry is to understand the relationships between what's happening in this molecular level and what's occurring on the macroscopic level. So this is a pretty simple example, but a good one to start off with.